Well, thank you all for coming. For those of you who don't know me, my name is Andrew Jones, and I work with Activated Research Company. So, how many of you have used packed columns before? Anyone? We got 1, 2, 3, 4, 5. Okay, how many still use packed columns? Got a few. 1, 2, 3, 4. Okay. Well, as many of you know, we've made a shift over the last 30, 40 years, in large part, to shift from packed columns to capillary columns. To get tighter separations, more theoretical plates, a lot of benefits of those, but there are still packed columns around for a few of the archival methods, so to speak. GCs have also changed. If you look at the 5890 and now recently the newly released Intuvo, there have been a lot of simplifications of GC, a lot of drivers to make analysis easier for the scientists, more reproducible, and more accurate. So what about detectors? What are the most recent changes that are bringing simplicity to analysis for us scientists? Well, let's take a look at the flame ionization detector. This is the most widely used detector for a number of reasons. It has a large linear dynamic range, over 7 orders of magnitude. It's sensitive to a large number of organic compounds, carbon. It also is very robust. It's not easy to break, and if it does break, it's easy to fix. It's pretty simple and very low maintenance. Here we see the amount of carbon injected for a molecule like methanol over about 4 orders of magnitude. We see that FID signal is about linear. This is a log-log plot. Now the problem with the flame ionization detector, or the FID, is that it has a non-uniform sensitivity to different carbon atoms of different environments. And this is the same problem that's shared with a number of other detectors, like the mass spec or the thermal conductivity detector, that the sensitivity of that detector depends on the types of molecules that it's detecting. Now that's not true for a sulfur SCD detector or a nitrogen detector, which are equimolar in their response to those species. But as of a few years ago, there had not been an equimolar response detector to carbon. So this non-uniform sensitivity causes us to have a need for calibration. So if you have a spectrum like this, which is from methanol to gasoline chemistries, you have hundreds, if not thousands, of different peaks, many different oxygenates or different heteroatoms. You need to calibrate this spectrum for each one of these different species to get an accurate quantification, to understand where your carbon is going, and that can be very difficult, or in some cases impossible. So there could be unknowns in this spectrum. Maybe the mass spectra database doesn't have anything, or you have no idea what these are. There could be expensive standards. The standards could be unavailable where you currently are, or just in general. And there's also error propagation steps every time you do a calibration, and it's time intensive, right? Nobody likes to do calibrations. So we asked, is there a better way? Could we enhance the flame ionization detector and bring an equimolar response for carbon as well? And what we came up with was a reactor that sits after your column. This could be capillary or packed. And you separate your molecules, and then they go into this reactor and get converted to a molecule that's the same for all these species, in this case methane. Now your FID is only counting methane. You have an equimolar response for all of your species. So as you can see, the flame ionization detector, which typically has order of magnitude different response for different carbon atoms, when we put our reactor in there, we're able to get an equimolar response for all species that we put into the detector. That means one calibration curve right here, a universal carbon response for all carbon molecules. We call this post-column reaction to methane, or the Polyarc reactor, which is shown here, and it sits right behind a flame ionization detector. And that sits right in line with the FID. So you have your column, and then a simple zero dead volume union, or an ultimate union, to the Polyarc, and then right into your FID. You can also add other detectors with different splitters to get the best of both worlds. So let's look at a specific case study of using this piece of equipment for the analysis of volatile organic compounds, which is probably interesting to a lot of people in this room. So here we look at methanol, TBO alcohol, MTBE, DIPE, ETBE, TAME, and TAEE. And we look at, this is the signal that we get with the Polyarc reactor in place before an FID. And we show it in comparison to a normal FID in the dotted lines. So you're getting the same separation, or baseline separation with this reactor, but you're getting a higher response to those oxygenates because we're burning those oxygenates more efficiently when they're converted to methane. So now we can dilute that sample over 7 orders of magnitude, and we can look at the response with the amount of carbon that we've injected onto that column. Now this was all done with an on-column injection to make sure we're putting the right amount on that column, so no split here. And we can look at the moles of carbon injected in picomoles from about 10 to the 1st to 10 to the 7th, and the integrated FID signal. And we see it's linear on a log-log plot. And then we can look at DIPE, all the other ethers, the other alcohol, toluene, other ethers. Any species that we put into this system, we're going to have this same universal carbon response with very high linearity, over 7 orders of magnitude in this case. So this eliminates the need to calibrate the differences in different molecules. You need to calibrate your system if you're using an external standard for this single curve for all molecules. You could choose hexane and it would work for methanol. You could choose toluene and it would work for purity, for example. If we compare this to a mass spec, the scatter is very wide. The order of magnitude range is quite a bit lower. We see a lot of tail off here because you start to ruin your ion source. And there's scatter, these are orders of magnitude ranges for different molecules because of the different response of the mass spec to those species. Now we can divide by an internal standard, and now we completely get rid of the need for calibration because the response of that internal standard on a carbon basis is the same for that species as well as any other species in that sample. So now this line, which goes through 0, 0, and 1, 1, is just the y equals x line, is true for all molecules. We're plotting right here the moles of carbon injected of our analyte divided by the moles of carbon injected of our internal standard. And we're showing, the FID signal for the analyte divided by the internal standard. And over 7 orders of magnitude, we see a very high linearity. So here's an example of a sample with hundreds of different compounds. This is 87 octane gasoline with 10% ethanol. And with the FID only, we see all of our peaks. With the Polyarc, we see a very, very similar separation. So we're not affecting your separation performance or your chromatography. And that's critical, of course, that we're putting a reactor in line with your chromatography. We had to make sure that we're not affecting the chromatography. You're getting the same peaks that you would have before in shape, but now they're bigger, more intense because you're converting everything to methane. We've also designed it to have a replaceable catalyst cartridge. Many of you might be familiar with methanizers, which require usually a change in catalyst over a certain period of time. Here we have a cartridge, which is quite easy to replace. So on the top, you see a new reactor, and these are very sharp peaks. You see basically the same performance as an FID. When your reactor needs replacement, you start to see tailing in those peaks. So it's a very clear indicator. You haven't affected accuracy, except that you start to tail and it becomes harder to integrate. So it's a very clear signal that you need to replace that reactor, and we have a cartridge you can do that with fairly easily. So what some of our customers are seeing out there are some big savings in terms of reducing the amount of calibration or even eliminating calibration completely when it can be done. And this is just a simple example of 30 minutes per day calibrating, $20 per week spent on calibration standards. Very conservative, very low numbers. Most people are spending quite a bit more. We have customers that spend $10,000 on a single calibration standard or cylinder, and the cost of our system is less than that. So you're actually paying for itself in one calibration. And so here they see about $15,000 in a conservative estimate of savings for a single GC. You also see an increase in sensitivity. I mentioned that we're converting everything to methane, and methane burns very well in an FID. It burns a lot better than your ethers and your fames and your methanol, and it burns a heck of a lot better than your formic acid, formaldehyde, formamide. Things with a lot of heteroatoms or a lot of functionality don't burn well in the FID. And when we can convert them to methane, that gives us a very high efficiency in the FID. CO, CO2, of course, aren't detected at all in the FID, and we're able to see them with the same sensitivity as methane. So as a methanizer, yes, it can be used as a methanizer. It is quite a bit more than that because we convert all molecules. But in place of a methanizer, you've probably seen the typical nickel methanizers, which just convert CO and CO2 to methane. Here we're converting everything to methane. We're getting equal molar response for all of our compounds. You don't need to use complicated valving to bypass the methanizer to avoid poisoning it, because you're not going to poison our reactor. And you can operate it very simply with detection ranges below 100 ppb up to 100% of your sample. Here was 5% CO and CO2 in a mixture of methane, ethylene, and ethane. And you see here with the FID, you don't see CO and CO2. With the Polyarc reactor in there, you see them with the same sensitivity as all the other beads. I do want to give a shout out to our booth. So we're in booth 5008, and we're doing a little demo of this, a live demo. So you can come, and we have balloons you can blow up and measure the CO2 in your breath. So it's pretty fun. It takes 30 seconds to do. So I'd encourage you guys to come by and measure your CO2. And you can hold your breath and see how much it raises as well. So just a little demonstration to show off the Polyarc. So here's an example of a number of different species that have been looked at. And you see with an FID, there's a wide range of different sensitivity or response factors to those species. And with our microreactor, we have a similar response with an error, and it's much, much higher than what you're getting with the FID. So we can also separate the stream. We can use a splitter, and we can separate that column to a mass spec and a Polyarc FID and get identification and quantification in a single injection without calibrations. This is an example with a 86 or 88 weight percent ethanol, so E85 species. We have a lot of data on our website. I can't go through all of it. Some of our customers have written app notes about what they've done to use Polyarc and some of the species that they've looked at. So I'd encourage you guys to go to our website or come to our booth and talk to us more. Sorry. So what we're able to do, with the Polyarc, this benefit of a uniform response is to be able to quantify without standard calibration. We can measure the FID signal and look at directly from that curve, we can get the number of moles of carbon that we injected, or the concentration. We can also look at discriminations from this to find leaks in our GC. We in general see better data quality because we know what to expect in our response. And we're able to analyze more compounds that would be prohibited with calibration. It's a simple data analysis. It's a single equation. Response factors are all one, so we're just looking at a single equation to quantify all of our species. So some of the examples that we've seen out there, this is from Paul Downhauer at the University of Minnesota. He saw a piano mixture with a number of different hydrocarbons and realized quickly that that mixture had a lot of errors in it. So the standard actually had errors in what it was made, and it was boiling off. So he quickly was able to make his own mixture and figure out that the Polyarc was diagnosing an issue with that standard that he had purchased. So ASTM D5501, able to quantify ethanol without calibration. And in conclusion, we're able to diagnose GC issues, sample issues, as well as look at species that we couldn't see before with the FID with better clarity and better accuracy. So please come by our booth, and we'd love to talk to you more about what we're doing at Activated Research Company. Thank you all for your attention.